So we're learning a new notation today. This is probably something you've never seen. And new notation is a strange thing because it can be very confusing. And so it seems hard. But then I try to differentiate between confusing and hard. They're not the same thing. Right? To me, hard is like something that's difficult to do. Like it's actually challenging. It's complicated. Right? Like calculus or something like that. Or hard would be climbing a mountain. That's actually hard to do. Whereas new or something that's new is just unfamiliar. So it's not obvious, it's not intuitive, and you just have to get used to it. Like learning a new language. When you're learning a new language, you hear all these words that you've never heard before. So it's not like hard, because if somebody told you what the word meant, you'd be like, oh, okay, that means cup, right? That's not complicated. It's not complex to understand, but it takes time to get used to. So this is going to look confusing a little bit at first, but it's only because it's new. It's not because it's hard. It's just a new notation. But then the other thing is like, why do we have this new notation? It was fine the way it was. I like the way we did it before because I understood it better. Fair enough. But that's the way things are, and there's a very good reason why we use the notation that we're going to learn today. Okay? So, it says, consider the function below. It has two variables. It has the input variable, which is x, and the output variable, which is y. And this is a straight line, so it would be a function. Okay? And what does it mean? I could do a little table of values here. So if I pick some, when we have these equations, I think we talked about this before, they're set up in a way that I choose the x values. I choose the input values. And then the equation generates the output value. This is probably something that your teacher talked to you about in elementary school and you probably didn't really understand it at the same level that you might now. And now it might be like, yeah, that kind of makes sense. So I'll pick 1. I'm going to throw that 1 at this equation. And the equation is going to throw, oh, it's frozen, thanks. That's what you're going to say, right? And I'm going to throw it at this equation. And the equation is going to give me back 3. Because what the equation says is, whatever number you give me, I'm going to multiply it by 3 and then give you the result. Right? What about 2? Throw the 2 at the equation. 3 times 2 is 6. Equation is going to give me 6 back. What about 10? Throw 10 at the equation. 3 times 10 is 30. Equation gives me 30 back. The point of an equation is representing a pattern like that. The problem is, in high school, we start to get equations that are more complex than we can just understand the pattern of, like in a simple way. And so we start to think that there's something fancier going on. Like we start to think that this algebra is too hard to understand. But all an equation is, like, what's the relationship here? 3 times as big. The y's are 3 times bigger than the x's. That's the relationship. Who in here doesn't understand that? You all understand that. You understand for something to be 3 times larger. That's what that equation means. One number is 3 times as large as the other. That's all it means. We get into quadratic relationships and other relationships, and they do get a little bit more complex, but they all mean something similar. It's just that relationship between two numbers, right? Okay, so that's what that relation means. It is a function, and we can throw input variables at it, and it'll give us back output variables. So what we say is the y value depends on the x value. Depending on what x value I give it, the y value will be different. If I give it a 1, the y value is 3. If I give it a 2, the y value is 6, right? So the y value depends on which x value I choose. So we call one the dependent variable and the other the independent variable. You may have heard some of this before. You may not. This is not the important part of what we're doing today. We're just talking a little bit about these relationships in general. Okay. So what would be some real life situations where you would have something that depends on something else? I'll give us the first one, at least the first one. Let's say this is distance and this is time. And you're going at a constant speed, so it would be a straight line like that. If you're running, how far you run depends on how long you run, right? See how in the real world, one of them naturally depends on the other. And this is why time has to go on the horizontal axis. You can't put time up on the top and distance on the bottom. This is just a convention in mathematics, but we always put the independent variable on the bottom. Independent variable always goes here. And time doesn't depend on anything. Time just goes. But the distance you travel depends on how long you've been going, right? Okay, what's another one? Anybody else think of another one? It can be easy to come up with them when time is on the horizontal axis. So if we keep time here, what else depends on time? Anybody think of something? Your height, which is a type of distance in a way. The distance the top of your head is from the bottom of your feet. But height, like you grow over time. Yep. Speed over time, that's acceleration. That's true. If you're accelerating, your speed is increasing over time. So that's very good. And in physics class, you talk about those relationships a lot and the graphs of them and that kind of thing. How about cost? What would be something that would be cost depends on time? Can anybody think of an example? And again, maybe it's going up like this. Jay?
I feel like renting out like a building, how many hours?
Very nice, yep.
It depends on how much you're going to pay.
Yep, right. Anybody think of another one? Because you could come up with lots of specific examples. Yep, good. Or along the same lines of business, working. Who has a job? And you make an hourly wage, is that right? So if you work 5 hours, you make a certain amount of money. If you work 8 hours, you make more. So the cost of your labor depends on time. Or it could be earnings. Depends on time. The longer you work, the more you make. Right? Not all jobs work that way, but part-time jobs usually do. So last one, I'm going to keep cost, but I'm going to change this to items. What does that mean? Well, if I go to the store and I buy 2 cookies, it's going to cost me $2. If I buy 3 cookies, it'll cost me $3. If I buy 10 cookies, it'll cost me $10. So the cost depends on how many items I'm buying. It doesn't depend on time. It depends on the number of items at the grocery store. Maybe it's not all cookies, maybe it's all of your items in general, but the cost is going to go up the more things you buy, right? Unless they got some kind of weird sale where if you buy 3, it actually costs less than buying 2. Happens once in a while, not very often. Okay? And again, the cost is going to go up probably as the items goes up. So again, this is just fundamentally what relationships are all about. They're all about representing something in the real world, but I can use equations to represent them, which makes it easy to come up with number values. And if I have $20 and I want to know how many cookies I can buy with that, There's your math right there. What you are doing is you're solving a simple equation. When you figure that out, and most of us do that all the time and we do it naturally, and then we get to math class and we say, I don't know how to do any math. But you're doing it all the time. You're just not aware of what you're doing. Anyway. Okay, let's get into what we're actually talking about today, and you'll kind of see why it's related. But so you've been doing this kind of stuff for a long time, and you always say y equals 3x or y equals x squared plus 10 or whatever, right? It's always y equals y equals y equals. That's the xy notation. It's simple. It makes sense for graphing because we graph with a y-axis. And in a lot of cases, it's totally fine. It's a good way to do it. Turns out there's another very useful way of sort of writing the same kind of thing, and it's called function notation. So instead of writing y equals 3x plus 2, I write f at x equals 3x plus 2. And this is why I started by saying, people say, what's the point? So instead of writing y, I write an f and an x. Who cares? How is that useful? Well, I'm going to try to explain a little bit of why that's useful. We're not going to worry too much about it. Turns out this is a big deal, and this is a big thing. And again, if you continued in mathematics, you'd see it all the time. Okay? So let's talk about it. F replaces y as the dependent variable. So the x part isn't part of the variable. The x goes with the x on the other side. And one of the great things about this is that we can use all the letters. So we can use f at x, g at x, p at x, q at x, r at x, d at x, t at x. Like x at x, probably not. Some letters are better as a variable than others. Like O isn't a good one because it looks like a 0. Sometimes S's look like 5s. Sometimes L's look like 1s. Like there's letters we avoid. And there's common ones that we use. We use F generally. And then we use G, we use H. And then there are certain specific places where we use other specific ones, like R at X is one that's used for something. But anyway, but for us, we'll use whatever, but we'll probably use kind of FGH. Why is that important? Well, if I'm talking about more than one relation or more than one function, and I call them all y, how can I tell you which one I'm talking about? I would just have to point at that one, the second one. But if I'm talking about 3 different functions, and I call them f, g, and h, then I can just say h, and you'll know which one I'm talking about. And that may not seem very interesting, but you can understand how that would be useful if you were doing something where you had many functions at the same time, right? And in this course, we probably won't do that too much, but we do in some grade 12 courses, we do that a lot. So it's really useful to be able to name functions with different names and then refer to them all in one question kind of thing. Okay, so that's the easiest useful way of seeing this. But the other thing, and again, this isn't going to be too important to us, but is it gets the y out of there, and f isn't so much a variable as it is the name of the function. And so now I really just have one variable. And that's what makes it a function. I only need one variable to talk about it. Okay? And so it all kind of just works together. So when it's the same thing, we pick x's, plug them in, and solve for the output, which we would call, I suppose, sort of the f value. So we're looking for the value of the function f at, the value of x. And I'm only writing this because this is how you'll notice we say, like we talk about this stuff. We say f at x, or some people say sort of f of x, f at x, f of x. And now what we know that to mean is it's kind of like we're solving for the y value. But it's not always just x. It could be f at 2, or f at negative 10, or f at 3. Like we can put actual values in for x. So it's just a new notation. It takes some getting used to. I don't think it's hard. It's just new. And if you're finding yourself asking, why are we complicating things like this? Well, don't worry too much about it. You'll have to take my word. It's a big deal, and it's a good thing in the long run. But whenever we're learning something new, especially new notation, it seems complicated at first. Practice a little bit, and you'll get it. And we're not going to do it. And again, we're not going to do anything really fancy with this. We are just going to sort of practice some of the more simple sides of it to get used to the notation. Okay? So this should be on the back of your page, is that right? The other nice thing about it, which I didn't write down, but we'll talk about right now, is it's really easy to show what value you're plugging into the equation. It's like so easy. So the y notation doesn't have this way, any way of doing that. It actually kind of does, but it's really messy, and it's not one you've seen. So you would just say, when x equals 1, find y. But instead of saying all of that, now I can just say f at 1. And what that means is I replace all x's. See how the question defines f? It's 4x plus 1. And I take whatever's in the bracket on the left side, and I put it in for all the x's on the right. So I'm going to put a 1 in there. And then BEDMAS, 4 times 1 is 4, plus 1 is 5. So for us, this is probably the most useful side of it, is it's a really simple, slick way of saying what value of x you're punching in, where you don't have to write out, find the y value when x is this. Just f at 2, f at 1, f at negative 2. So again, 4, and in the brackets, I put negative 2. Negative 8 plus 1, negative 7. F at half. Oh boy, fraction math, oh no. Multiplying by a half is the same as dividing by 2. You're just taking a half of something. So I think you all know what half of 4 is. There will be some fractions that pop up throughout this course. If you really dislike fractions, I would strongly encourage you to get a good calculator that does fractions very well. Like this one. 4 times, hit the fraction button, 1 over 2. It even looks like the way the question looked on the page. Or instead of the multiplication symbol, I could have used brackets and make it look exactly like that. Okay? Hit equals, gives me 2 there's rarely a time where I need to see any steps of fraction math at this point. So if you don't like fractions, you can just power through them with your calculator. All right, let's keep going. So now I've got a different function, h. And this one looks like it's quadratic. Remember, the h at x replaces the y. So for you last year, this would have been y equals 2x squared minus 3x plus 1. But now we're calling it a function. We only use function notation, by the way, for functions, right? We wouldn't use this notation if something wasn't a function. We wouldn't use this notation for a circle. You kind of couldn't because a circle requires two variables. Remember, the circle was x squared plus y squared. So it's got to have that y to square it. Okay, so again, we're replacing all variables. This got two x's in it, so both of them get replaced by 5. BEDMAS says I do exponents before anything else. You probably know that we could have done that multiplying on the same step if you wanted to. It's a bit less writing to write 15 than writing that out again. 2 times 25 is 50, minus 15 plus 1. That looks like 36. A couple more. Negative 1 all squared is positive 1. Be careful, if you type this in on your calculator wrong, negative 1 squared, you're going to get the wrong answer. So this is why sometimes it's better to do some of the simple math in your head, learning the rules. But if you type this in the correct way, you could do all of this in one shot. Whoops. Negative 1 plus 1. So it should work out to 6. Negative 3 times 1 is 3. Looks like 6 to me. Okay, one more. It's a decimal. Decimals aren't different than other numbers. So I do the same thing and I just punch it in there. And again, for a question like this, you don't have to show steps. You can just punch it into your calculator. But it can be interesting to see what happens. The only way we're going to get better at numeracy and understanding numbers and better at mental math is by doing it a little bit at a time. So if you don't know what 0.1 squared is, then do it on your calculator. 0.01. Okay, and 3 times 0.01 is 0.3 plus 1. So I get 0.02 minus 0.3 plus 1, which I believe works out to 0.72. Any questions? Next question is a little bit different. So this one's asking us to find the value of t. When you're given d at t. So you used to do this, you had to find x when you're given y, or find y when you're given x. We always have to know how to do both. But because this is new notation, this seems a little bit strange maybe. But it's giving me d at t, so I sub that in on the other side. So this just means 7 equals 3t minus 2. That's all that means. And then I solve for t. So just watch it, because sometimes people just don't understand that they don't read the question, they just start solving, and they put 7 in for t the way we were doing above. Okay, and that would give you all the wrong answers. So add 2 to both sides to get 9 equals 3t. Divide both sides by 3, and t is 3. Couple more. So negative 8 equals 3t minus 2. Now what's interesting is it's always going to be 3t minus 2, so it's always going to be the same 2 steps. What did I do in the first case? I added 2 divided by 3. Well, that's what I'm going to do again. I'm going to add 2, but now I'm adding them to a negative, so that should give me negative 6. Then I'm going to divide by 3. Negative 6 divided by 3 is negative 2. So t is negative 2. Last one, add 2, 5 plus 2 is 7. Divide both sides by 3. 7 divided by 3 is 7 over 3. Or 2.3333333 forever, right? So we would leave this as a fraction. Here's my rule of thumb. Every teacher's maybe a little bit different. If you get a fraction like 5 over 2, and you write it as 2.5, you will never lose marks for me. I guess if the question said leave your answer as a fraction, I would maybe have to take off half a mark. But honestly, I don't care as long as it's a strict decimal. But if it's a decimal like this, that's repeating, unless the question says round to 1 decimal place, round to 2 decimal places, you should be leaving that as a fraction. Okay? So this one should be left as a fraction because it didn't say round. But if it was 5 over 2, 5 divided by 2, you get 2.5. Yeah, you can write 2.5, that's fine because it's exact. You haven't rounded, it's a perfect answer. Okay, so that would be my rule of thumb. Any questions? New notation takes a little bit of getting used to. But you can see that the actual math that we did with it was fairly straightforward.